Okay, so the first kind of problem that we're going to have is what's called a mixture problem. And so I'd like to kind of make a visual on how these things really work. Sometimes the models, the equations get kind of confusing or so, and I'd just like to kind of point out where these things come from and take a simple example like red balls in a bag and mixing two bags and see, how do these equations work out. So let's say we have two bags of balls and we're going to mix them and put them in a third bag. Okay, so some of them are red, and in the first bag has 12 balls in it, the second bag has 8 balls, and so when we mix them together, clearly we have 20 balls. Now if we count up the red ones, we have 3 red ones from the first bag, 5 from the second, and so when we mix them together we get 8 balls. Okay, so this is just plain basic stuff. But let's look at percentages now. So in the first one we had 3 divided by 12 is 25%. So 25% of them were red. Second one was 5 divided by 8, which is 0.625, or 62.5% are red. And what we end up with when we mix them is 40%. So if you look at those 3 numbers, okay, we got the numbers in black are the totals, the numbers in red are just the red balls by count, and then the greens are the percentages. The percentages really don't relate to one another directly, right? We can't take 25%, add it to 62.5% and take the average. You would think that might be a reasonable approach to do, but it doesn't work. So what we need to do is work really on the first 2 lines of everything. Now, generally when we're dealing with mixtures, we'll know a concentration or a percentage that something is in another, like antifreeze, might be an antifreeze, 40% antifreeze, 60% water, things of that sort. We don't have a count of the ingredient. So what we're going to do is make the equations work so we're in essence calculating the amounts of the ingredient. So if we notice that if we don't have 3 available to us, but we know that 12 balls, among 12 balls there's 25% of them red, well, we just multiply 25% times 12 and you get 3. And so if we write up a total equation on how this works, so this is the equivalent of 3 plus 5 plus 8, we're taking the concentration in the first bag times the quantity of the second bag, the total quantity, and then the concentration in the second bag times the total quantity, and we get the ultimate concentration with the mixed bag. Okay, so this equation and this top one, this 12 plus 8 equals 20, are really the 2 equations that we have to work with solutions, and so we'll have a little practice manipulating those. Okay, so let's put this in a little bit general context here. And so we have a volume of A and a volume of B. We mix them together, we get a total volume. And then that second equation is we have a concentration of A times the volume of A. So that's the amount of the ingredient in A. Okay, it's not the amount of A. A is a volume. And then if we multiply the concentration times the volume, we'll get the amount of that ingredient. And then we're going to add the concentration in B to the volume of B, and so we'll get the amount of our ingredient in B, and so then the last one is the concentration of the mix times the total volume. All right, so let me write this up here just to, this will be useful when we're doing some examples. So we have a volume of A plus the volume of B equals the total volume, and then we have the concentration of A times the volume of A plus the concentration of B times the volume of B equals the concentration of the mix times the total volume. All right, so we'll hold on to that for the examples. Now, a couple things about them is that in order to use these, okay, so we have this model now. We don't need to invent a model. We have this one. We can solve all sorts of problems just by going through and defining the variables of the things that we don't know, and then establishing the amounts of the things that we do know. And so ultimately what we want to do is make an equation with one variable. And so what we're going to do is, instead of using the total volume, we're going to use the total volume as the volume of A plus the volume of B. So that's going to be right in here, and that'll usually drop into some parentheses like that. So we make sure we distribute that concentration right. Okay, so let's do an example. So we have a 2-pound bag of mixed nuts. It contains 20% cashews, and a 3-pound bag of mixed nuts contain 10% cashews. So when you mix them, what do you get? What's the percentage of the mix in cashews? What percentage of the mix is cashews or are cashews? Are cashews, right? So this is not an English class, thankfully. Okay, so now whenever I'm doing problems with nuts, I'll generally throw in cashews because that's my favorite nut. So that's why I'm using cashews and not peanuts or Brazilian nuts or whatever. Okay, so let's go through, use this model. So we know the total weight is going to be the sum of the two bags, and then we have our cashews. We look at just the cashews, so we have a percentage cashews in A times A, percentage cashews in B times B, and that'll give us the weight of cashews in the mix. And if we divide, and if we divide that by the total mix, then we'll get the concentration, okay? So the first line is easy, 2 plus 3. I'm going to end up with 5 pounds of nuts. And then I'm going to take my equation, 20% of the first bag is cashews, so 20% times 2 will give me the amount of cashews from the first bag. And then we have, this is a 0.1, I know it looks kind of funny, but it's 0.1 times 3, so 10% of 3 will be 0.3. That's how many pounds of cashews we get from the second bag, and so we add the two together, and we get 0.7 pounds of cashews. And so if we want to find what the percentage of the mix is, then we take 7/10 of a pound divided by 5 pounds is the same as 14 over 100, or 14% cashews. Okay, so hopefully that's straightforward enough to follow. Yeah.
Can you go back to that last slide just for a second?
Mm-hmm.
Why did you divide it by 5?
Because the question was, when you mix these, what percentage of the mix is cashews? And what I found out in the equation was how many pounds of cashews do I have? So I took the concentration times the volume, concentration times volume. I'm really looking for the concentration, but what I got, if I multiply these two together, is I get the number of cashews that I have. So I could make that first equation look like this, where I say 0.2 times 2 plus 0.1 times 3 equals, and then I'll say the concentration, I'll say C is the concentration in mix, and so I'm going to have C times the weight of the mixture, which is going to be 5. And so when I calculated this, I got 0.7 equals C times 5, or 0.7 times divided by 5 equals C. So I just left that off, okay? Just to kind of illustrate what we're really calculating with the second equation, the one with all the percentages, is that we're just counting up our cashews, just like we were counting up the red balls in the very first example. Okay, so everybody have this? Can I move on now? All right. So let's do another example, and then I'll have you try one. So you have a 10% solution and a 60% solution of antifreeze. And how much of each do you put in to make 10 gallons of a 50% solution. Okay, so we have two different unknowns here. We don't know how much of the 10% solution, and we don't know how much of the 60% solution we need to put in. But we know that the total is 10. And when you know the total of something and you establish the variable in for one item, don't make another variable. So here I'm going to say x is the number of gallons of the 10% solution, and then I'm going to say 10 minus x is the gallons of the 60% solution. If I say y is the number of gallons of a 60% solution, then I have another equation, x plus y equals 10. So why bother with y to begin with? If we know x, or we're going to solve for x, then we can get the other one by saying 10 minus x, because we know when you add them together you get 10. Yes?
Wait, why is it 10 minus x?
Well, on this next line, if I add the two together, so let me do this, okay? If x is the 10% solution and y is the 60% solution, we know that x plus y equals 10. And if I subtract x from both sides, I get y equals 10 minus x. So why bother with y? I'm just going to write 10 minus x. So if I know I have 4 gallons, I know this is going to be 6 gallons. And if I have 2 gallons, then I know this is going to be 8. Okay? So it's really just being conservative about how many variables you have out there. If one variable will do, keep it. Don't introduce other variables if you can make expressions in that first variable. Okay, so let me write the equation now, and this comes right from this second line. The concentration is 10% times x, which is the volume of the 10% solution, times 60%, and then this is going to be 10 minus x. Make sure you use parentheses so everything works out well. And then what you want is a 50% mix of 10 gallons. All right, so that's the end of the equation. So we have one equation, one unknown. We should be able to solve this. And so you have 0.1x plus 6 minus 0.6x equals 5. So the first step here, I just distributed the 0.6. So 0.6 times 10 is 6. 0.6 times negative x is negative 0.6x equals 5. So the first thing I'm going to do then is take 0.1x minus 0.6x, and what I get is negative 0.5x. And then I'm going to subtract 6 from both sides. And so I get 5 minus 6, or I get negative 1 over 0.5, which is 2. So you need 2 gallons of the 10% mix and 8 gallons of the 60% solution to make 10 gallons of the 50%. So let's put that in our equation and see if that works out. Just to test it, if we say, okay, a tenth times 2 plus 0.6 times 8 equals 0.5 times 10, and sure enough, we get 0.2 plus 4.8 equals 5, 2.2 plus 4.8 equals 5. So it checks out. Okay, so it's time for you to do one now. Okay, so you have 2 gallons of a solution that is 25% cleaning agent. Do you ever notice when you look at a bottle of 409 or anything like that, you can't find the ingredients on there? You ever wonder about that? How do you get away with that? All right, and then what we want to do is we want to add pure cleaning agent to get a 50% solution. question is, how much do you need to add? Okay, so I have a 25% solution, and I have the pure stuff. I want a 50% solution, so I'm going to pour in the pure stuff until I get to 50%. So how much is that? And these are going to be known as distance rate problems. And so here we have probably the simplest model of all that we're going to be dealing with is rate times time equals distance. And you know that from a car, right? So if you're going to drive 25 miles per hour, it's okay, 25 miles per hour for 2 hours, you know you're going to go 50 miles, right? So this is just straight multiplication. So let's do an example where we can use this model. And so let's say Bill is walking 3 miles per hour and Sue is riding a bike at 15 miles per hour. Okay, so Bill starts walking, Sue starts riding 45 minutes later. When does she catch up with Bill? Okay, so the first thing that you know about this is that they've gone the same distance. They're going different speeds and at different times. And so we just need to make use of that rate times time equals distance. So we know that Bill's distance equals Sue's distance. All right? And then we're going to define, we don't know how long Bill is traveling, so we're going to say Bill is traveling at T for T hours, and he's traveling at 3 miles per hour. Okay, so there's one thing that we have to make sure of that we do in here. We're dealing with hours and miles per hour, and Sue is starting 45 minutes later, which is 3/4 of an hour. So we make sure we're in the same units. Okay, not a big deal to change, but we just make sure that we're consistent there. All right, so let's see what Sue is about now. Sue's travel time is going to be Bill's travel time minus 3/4 of an hour. So if Bill travels an hour, Sue travels 15 minutes, you know, that sort of thing. And then Sue is traveling 15 miles per hour. And so now we just use our the equation that I have up here, where Bill's distance is 3 times t, and Sue's distance is 15 times her time, which is t minus 3/4. And so one equation, one unknown, we solve for this. So first thing we do is multiply through by 15, so we get 3t equals 15t minus 45 over 4. And now I'm going to multiply through by 4 to get rid of that fraction. So 4 times 3 is 12, 4 times 15 is 60, 4 times negative 45/4 is 45. And then I get 45 equals 48t. So I need to reduce that, and so I factor it, and I notice that I get 16/15 of an hour. And so how much is a 15th of an hour? Well, 60 minutes divided by 15 is 4, so a 15th of an hour is 4 minutes, so we're going to go 1 hour, 4 minutes. 1 hour, 4 minutes for Bill. Okay, so then what we have to do is subtract 45 minutes, and that'll be Sue's travel time, right? So I can write my answer as Sue catches up to Bill when Bill has walked for 1 hour, 4 minutes. Sue rode 19 minutes to catch up. Now notice this question doesn't really ask it, when does she catch up with Bill? It doesn't ask from a certain time perspective. You could easily define t as Sue's travel time and then t plus 45 as Bill's travel time. But what you'll come up with then is that t equals 19, and then you add 45 to it to get Bill's time. Okay, so let me pause here. And what we're going to talk about now are work rate problems. Now, work rate problems are a little bit like distance problems in that we're going to have somebody who's working at a rate for a certain amount of time and they accomplish a certain amount. Now, that certain amount that they accomplish sometimes is just one, which is one job. So let's look at this case. So Katie can mow a lawn in 2 hours. Lynn can mow the same lawn in 3 hours. How long will it take if they work together? All right, now they're not going to just divide it in half, and since it takes Lynn longer to do it, she's going to work longer than Katie. That's not the way we're going to do this. They're going to work the same amount of time at their own rates. All right, so the thing that we want to do is say, okay, how fast are they working? All right, so this is a modification of the rate times time equals distance thing. This is going to be rate times time equals the amount of work done. And the rate, therefore, is the amount of work done over a period of time. So let's look at Katie's rate. So Katie is going to do one job in 2 hours, or she's going to do a half a job per hour, right? So think in terms of rates rather than the amount of time that it takes her to do it. So then what we don't know is Lynn's rate. Oh yeah, we do. It's one job in 3 hours, so it's 1/3 of a job per hour. And they're going to work about the same amount of time. So if I define T as the time they work together, I'm going to say, okay, Katie's 1/2 times time plus Lynn's 1/3 times time will equal, they're only going to do the one job, so it's going to equal 1. So this is what our equation ends up looking like. So there's Katie's work, there's Lynn's work, and we're doing one job. Okay, so now we can solve this. Multiply both sides by 6 is probably the easiest thing to do. All right, so then the 2's cancel on the first one, and we get 3t, and the 3's cancel, and we get 2t plus 6. And so we get 5t equals 6, t equals 6/5 of an hour. 1/5 of an hour is 12 minutes, right? 60 divided by 5 is 12. So they can do the job together in 1 hour, 12 minutes. Okay, any questions on that? So let me put up a problem for you to work now. Try the same thing where you are trying to consider the rates more than anything else. Okay, so Bill can paint it in an hour. If they work together, it takes 36 minutes. How long will it take for Jim to do it alone? Before you get too deep into it, let's think about estimating an answer, or where you would expect the answer to be. All right, so if they worked at an equal rate, you would expect that it takes them together 1/2 the time it takes for them to work individually, right? So if Jim worked the same rate that Bill did, this 1 hour would be 30 minutes, but it's actually 36 minutes. It's a little bit longer, right? So you would expect that it takes Jim a little bit more than an hour to paint the room. All right, so, think about that. So you have an expectation for a number that's going to be something over 1 hour. It's probably not going to be 10 hours or anything like that, because then he's not going to make too much of a difference. But, think of something close to 1. So This one is very similar to this problem, except that the variable now is the second rate, it's not the total time. But see if you can set it up just about the same, in the same fashion. Did you get something?
No.
No? Anything?
Yeah, 1.2 hours.
1.2 hours, okay. Okay, so how did you get that?
I did, so Bill was one job over 1 hour, and Jim plus Bill was one job over 36 minutes.
Okay, so 1/1 is Bill's rate, is what you said, right?
Mm-hmm.
Okay, and then,
1 over 36 was Jim and Bill's rate together. So then I did,
1/36, so here we're doing it in hours, right? One job per hour, and here it's one job per 36 minutes?
yeah,
Okay, so that's not consistent there, right? Okay, anybody take a little different approach?
Well, as far as I got, I just did like 1/60 minutes as Bill's rate.
Oh, okay, so you did it like this then. All right, this is good, because then you have minutes, right?
Yeah, but then I got stuck when I was setting it up, because I tried to set it up like that, so they were both doing one job, so the whole thing was gonna be equal to 1, but I didn't know where to put the 36.
Okay, so let's go through, well, I guess I erased it, but we can still see it on the board here. Let's say we do it like this. So we know Bill's rate, and we really want to know Jim's rate, right? So we can say R equals Jim's rate, or we can say 1 over Jim's time, okay? But let's go with Jim's rate right now. So if I do this, I know it takes 36 minutes equals time together. Where this combines now is I can take 1/60, which is Bill's rate, times the amount of time that Bill's gonna work, plus Jim's rate, which we don't know yet, times also 36, all right? And that's going to equal one job. All right, so how does that look? So let's, first thing is, let's just solve this now. We get 36R equals 1 minus 36 over 60. And then we're going to take R equals 1 minus 36 over 60. And then going to divide this by 36 or multiply by 1/36 like this. Okay, so the rate is going to be 1/36, and then this, if we multiply this together, we get, cancel the 36, we get 1/60. So if we subtract those two, we'll get Jim's rate. All right, so let's make a common denominator. Probably a 36 is 6 times 6, and 60 is 6 times 10. So if we multiply everything by, we have 60 in common, the common denominator is going to be 6 times 6 times 10, or 3,600. So we're going to say this is going to be 10 over 3,600 minus multiplied by 6, or 6 over 3,600.
On tests, we won't have numbers like this, right?
Well, I'm showing you how to work through them,
Oh,
okay? So we have a common denominator, so the rate is going to be 4 over 360. And so 4 divided by 360 is going to be, this is 9 times 4 is 36. So we get 90 minutes. Or this is going to be 1 over 90 is how that reduces. And since this is the rate, one job in 90 minutes, we get 90 minutes is Jim's rate. Or Jim's time alone, I should say, is 90 minutes. Okay, so was that reasonable? Well, I was looking for a number that's somewhat over 1 hour, and 90 minutes is an hour and a half. So it's perhaps reasonable. So how do we avoid all these numbers now? The way that we can avoid the numbers is by perhaps looking at these fractions a little bit differently. So if the time together is 36, we can, well, we're still going to end up with the same kind of calculation. I was going to suggest that we put it in actual hours. So this would be 6/10 of an hour. Okay, so the alternate equations that you would do would be 1 times 6/10 of an hour minus R times 6/10 equals 1. And so if I multiply straight through by 1, or by 10, what I get is 6 minus 6R equals 10. Negative 6R equals, am I doing this right? 6/10 is the time. 1 over 1, the rate, and that's going to be an hourly rate. So we get, subtract this. I'm going to get a negative number here, which doesn't make sense. I'm sorry? Oh, this is supposed to be plus, that's right. We're adding time. So then this is going to be 4. R equals 4/6, which in hours is 2/3 of an hour. So I'm still wrong here. Yeah, probably minutes is the way to do it. I haven't thought about it that carefully in doing it. And if you do in time together, this is 36/60, which is 6/10. So there's the time together, and the rate is still 1 over 1. Well, anyway, I'll clarify this on Friday. I feel like I'm just kind of going, just winging it, but with 36 minutes, it does definitely work. Now, the question about a test. If this kind of thing you should be able to do, all right, And if this comes out to a weird number, this fraction is perfectly good. So the reciprocal of this, or 360 over 4, is the amount of time, and that's fine. You don't have to make decimal numbers, but just have your integer ratios together. Okay? And I think that's about it for today. The problems that you're going to have are going to be those 3 kinds of problems: the mixed problem, the distance, the rate and distance problem, and then the work rate problem. You'll have. Did we what?
We just leave our homework in our notebooks?
No, I was going to suggest that too. The homework that you have has 2 labels on it. One of them is like WW1, WW2. That's the wet work, and so you work that in your notebooks, and you answer it on the computer. Your score gets accumulated on the computer, and on test days, you bring in your notebooks, and I'm going to look them over. On the ones that are labeled A, like A1, A2, A3, those are ones that you just turn in. Okay, you write them on a separate sheet of paper, turn those in, and then I'll give them back to you after I grade them. Okay, so on the ones where I want to see work, like word problems and things like that, they'll normally be the questions that are on the written assignments, and then web work will be the ones that are more calculation based. Okay, so you should have your homework and turn it in here. And I don't think I collected homework on Monday either, did I? So if you have it, turn it in. If you don't, bring it with you on Friday, and then it won't be counted as late because I forgot to ask for it. Okay?